Hi, my name is Urvi and my mentor is Omer. I am from San Jose and my project is evaluating design specifications for an activity-specific prosthetic arm to aid mechanics. So why did I choose this project? Thousands of people are affected by amputations every year. An amputation occurs when a physical part such as a finger, toe, hand, foot, arm, or leg is lost or removed. Upper limb amputations affect millions of people worldwide and in the United States. As of 2008, around 3 million people worldwide have had an upper limb amputation, and this makes up 30% of all amputees. 1.77 million have had an amputation below the elbow, 0.84 million have had an amputation above the elbow, 0.24 million have had a shoulder amputation, and 0.15 million have had a hand or wrist amputation. The use of mechanical tools is one of the leading causes of upper limb injuries. Around 22% of amputations are due to tools, parts, and materials. The aim of this work is to make a prosthetic for people who work in professions that involve hands-on mechanical work and who have suffered a work-related amputation. This activity-specific prosthetic allows for the tool to be attached to the prosthetic to perform the job with reduced risk. This work provides hope for those with a work-related amputation to return to their profession. These user needs listed in the table were decided based on the ones that could be the most beneficial for amputees working with tools. They were chosen after reading and reviewing multiple papers on how prosthetics are normally made. Computer-aided design, or CAD software, was used to design prototypes with these user needs for the activity-specific prosthetic. The first user need that my mentor and I decided on was maintenance, and we wanted the upper arm and forearm to be made out of titanium, which is a washable material. The next one was rotation, and we wanted the elbow and wrist to be able to rotate due to their joints. Next one was weight, and we wanted the materials and joints to be lightweight so they aren't difficult and don't have a high user abandonment rate. We also made sure that the size of the prosthetic and joints were small so that they would be able to get into small places and still be able to do work. Since this is a prosthetic for people who work in professions with tools, we wanted the terminal device to be able to do work with different tools, so we focused on the applications. The last one was a custom fit, and we decided that the device would be made out of titanium, which is designed to fit the user perfectly. These are the results for the prosthetic device designs that my mentor and I came up with. The first image on the left shows examples of a terminal device for the activity-specific prosthetic arm. Some of the tools that we came up with were a wrench, pliers, hammer, and a screw or a drill from left to right. The pliers and the screwdriver or drill can be electrically powered. The second image are the degrees of freedom requirements for the prosthetic arm and were found in one of the research papers that I reviewed. The last image shows the components of the activity-specific prosthetic arm. As for the mechanical components, for the shoulder, the best shoulder joint would be the one with 3 degrees of freedom shoulder articulation, 2 actuated joints, and 1 passive joint. This would match the rest of the joints, and it is the best type for this prosthetic. The example is the figure in the middle. For the upper arm, the optimum material for this kind of prosthetic is titanium, since it can be made to fit the person and retain an activity-specific prosthetic. It also has a low density, is lightweight, and has a high strength-to-weight ratio. It also has a great resistance to corrosion. As for the elbow, the New York electric elbow is the best elbow design for this prosthetic because it is compact and can turn 135 degrees. This is enough for the terminal device as it can be used for many different tools, and it can also work for 8 hours, meaning that it will work for the whole workday. For the forearm, titanium is the best material for this type of prosthetic because it will be able to be designed to fit the user and will be able to hold the activity-specific prosthetic. Additionally, it is low in density, light in weight, and strong in its relation to weight and density. It also has a high corrosion resistance. For the wrist, a passive wrist prosthetic with joints S and P. The joints S and P will allow the wrist to rotate and move forward and backward. This will be useful for the amputee as they will be able to do work required for someone who uses tools, parts, and other devices. Lastly, for the terminal device, several terminal extensions were designed to allow the prosthetic arm to attach to a variety of mechanical tools, as shown in the figure in the left. This work represents the first attempt to design an activity-specific prosthetic for performing mechanical work. Several design concepts were evaluated for the activity-specific prosthetic device. After 12 weeks, several design approaches for this prosthetic were considered. The work presented suggests that it is feasible to manufacture devices and end pieces for the prosthetic to fit different users. The prosthetic can be made out of a material that can be fitted for every person and can satisfy a wide spectrum of needs. This work is mostly theoretical. Therefore, more experiments using physical prototypes are required to assess the feasibility of the design. In the future, we plan on manufacturing the prosthetic based on the aforementioned user needs and the design criteria. This is the first design, so based on trials, the design will be enhanced so it can better accommodate the user. Rapid prototyping can be used to customize designs for different types of patients, which could reduce the cost. Thank you, and here are my references.